Hello everybody, my name is the Draft Doctor and today's layout is going to be an oblique cone and we're going to lay this out by using the triangulation method of pattern development. First of all, I'll just explain what an oblique cone is. It's simply a cone whose center line is not perpendicular to the base. If you look at my shop ticket here, you'd see the center lines would be on an angle not perpendicular to the base. Makes this an oblique cone. Typically there's two types of layout procedures that we can go to when we are laying out an oblique cone, and one is radial line development. Radial line development is a fast and accurate and easy way to lay out this piece. However, in order for me to use radial lines, the apex has to be within a working distance. When the apex of this cone is off the page or somewhere on the next block, I cannot lay it out with radial lines. Therefore, I must triangulate. Triangulation is the go-to for most difficult layout, and it is quite simple. The method of triangulation is defined as finding 2 points from a known point. Pardon me. So, here's the fitting that we have. 7-inch round, and it's tapering to 4-inch round. This fitting is 10 inches long, and the left has an offset of 1 inch, making it oblique. A couple of things I'm going to need to know for this particular layout is, number one, I have to find the 1/12 spacing for both the 7-inch round and the 4-inch round. So what I've done is I've taken the quarter circumference, which is pi times the diameter, divide 4, and for the 7-inch round it equals 5.5 inches. For the 4-inch round it's going to equal 3 1/8 inches. So what I did is I laid out two parallel lines and a perpendicular intersector at 5.5 inches. Once I laid out those those parallel lines, then I just took my scale rule, and on the full scale I found a diagonal that is equal to 3 inches. I marked those 1 and 2 inches there, plumb them up to the horizontal line, and what I have is a 1/12 of 7-inch round. For the 4-inch round I did the same thing. I laid out a 3 1/8 inch lines parallel to each other. I used the diagonal. This time I had to flip to the 3/4 inch scale to make it work, and it doesn't matter what scale I use. Here's the 3/4 inch scale. I lean it over. I've got 0 there, 3 there. I mark 1 and 2, plumb them down to this baseline, and I have 1/12 of 4-inch round. So I got all my necessities in order here now. I'm going to next have to lay out a working drawing. Now, a working drawing, we're going to lay this out from the plan view. I could lay it out from the elevation view. I chose the plan view today. Elevation view will be a different lesson, I suppose. Now, it's important for me to next divide the rounds on my layout into its 12 equal portions, so they will all equal the 1/12 spacing that I did earlier. Now, in order to do that, I simply take the radius that I use here for the 4-inch, and on each quadrant I'm going to intersect those arcs, and I'm going to do that from all 4 quadrants. Once I've completed all 4 quadrants, this will give me 12 equal spaces around the 4-inch diameter. Now, using the center of the 7-inch round, I'm going to switch to the 7-inch diameter, my 3.5 inch radius, which is right here. And now I'm going to divide my 7-inch circle into its respective 12 divisions. 1/12 spacing is common to all round layout, whether you're using parallel lines to lay out a round elbow or triangulating or radial lines. You're always going to be doing this. So including the quadrants and the radial lines here, I have 12 spaces around there. Sometimes you might even take it to 24 spaces. I had to lay out a helix once years ago, and in order for me to lay it out properly, I had to go to 24 spaces because it was 12 spaces. It was just rising too fast and it didn't work. Now, here's my seam. Seam usually goes on the short side. If I take this one center line and I draw it all the way through, the first thing that I'm going to realize is I have a symmetrical layout. 1/2 is equal to the other. Therefore, if I start at this point, whatever I lay out on this side is equal to this side, and I can just build it both ways until I reach the seam. So my first step is to find this point here, and what we're going to do is number this so that it makes sense to us. And what I'm going to do is call this 1. I'm going to go up here and call this 2. I'm going to come down here and call this 3, 5, 7, 9, 11, and 13. Likewise on the other side, 1, 3, 5, 7, 9, 11, and 13. The 4-inch circle will be 2, 4, 6, 8, 10, 12, 14, 4, 6, 8, 10, 12, and 14. I'm going to triangulate by going 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, and all the way around until we get to where we're going. So my first step in this layout, I'm just going to start with a line that is vertical. Nice and light. I'm going to take the bottom of that line, and I'm going to call it 1. I found my point 1. In order to find my point 2, I need to triangulate this fall from 1 to 2 over a 10-inch height. So what I need is a true length triangle. True length triangle, simply I need to build a 90-degree grid, which I have right here now. Oops, that slipped. Come in a little bit now. And what I'll do is I'll measure my 10 inches in height on my 1/2 inch scale. So from 0, this now will represent the height of my fitting right here. If I was to take my plan view of 1 to 2, plan view of 1 to 2, and now I'm going to triangulate that plan view of 1 to 2, and its true length is the hypotenuse that we find when we plot it on our true length triangle. It's falling this much over these 10 inches. Its true length is that hypotenuse. So now from 1, I can plot point 2. I have 2. Well, if I have 1 and 2, it should be pretty easy for me to go to 3 and 4. If I take my small dividers and set them up with my 1/12 spacing on my 7-inch round, I can quite simply put an arc on that side, and that somewhere on that arc will be 0.3, somewhere on this arc will be 0.3. My 1/12 spacing for my 4-inch round is set on this bow compass, and somewhere on this arc will be 0.4, and somewhere on this arc will be 0.4. I'm going to go back to my working drawing and do a little triangulating now. I've found 1 and 2. From 1, I've located 3. It's on that arc. Now from 2 to 3, if I was to take my plan view of 2 to 3, plot it on my true length triangle, there's 2 to 3. Here now is the true length of 2 to 3. Right there. And from 2, I can find 0.3. And from 2, I can find 0.3. Here is my 0.3, 0.3. I can quite easily find 0.4 by doing the same process now. I know where 3 is. I've marked 4 from 0.2. So from 3 to 4 on my working drawing, which is also the plan view, is this distance. It's not a true length. It needs to be triangulated over the height of the fitting, which is here. So this now becomes the true length of 3 to 4. So from 3, I mark 0.4. From 3, I mark 0.4. Back to my 1/12 spacing. From 0.3, somewhere on this arc will be 5. From 0.3, somewhere on this arc will be 5. And on the top, from 0.4, somewhere on this arc is 6, and somewhere on this arc is 6. And 1, 2, 3, 4, next would be 4 to 5. From 4, 2.5 has a plan length right there. That needs to be triangulated over the full length or height of the fitting. And here now is the true length. From 4, if I label my marks on my layout as I go, all I need to do is count to know where I need to swing this arc from. I'm looking for 5. I just found it. Here's 5. I'm going to document it. So next time I come back here with the true length, I know where to swing it from. From 5, I want to find 6. So here we are. 5. From 5 to 6 is this distance once again. 5 to 6. Here's the plan length of 56. Here now is the true length of 5, 6. Oh, look at it, I guessed right on. And I come to my drawing. Oh, there's 5. Bingo. I mark my 6. 5. Mark my 6. Document. 6. 6. My 1/12 spacing. 7 will be somewhere on that arc. 7, somewhere on that arc. Back to my smaller 1/12 spacing for the 4-inch rounds. 0.8 and 0.8. From 6, I need to find 7. There's 6. 7. I need to triangulate that. There is my true length. Come back to my drawing. There's my highest number, 6. Must be looking for 7. There's my 7. From 6, there's my 7. Document. 7. 7. From 7 I can find 8. Here now is my plan length of 7, 8. Plan length 7, 8. Plan length 7, 8. And true length 7, 8. True length 7, 8. And here is 8. And here is 8. Now, there's some telltale signs that can help us out as we're going through this process so that we don't make a mistake and know it's wrong. If I make a mistake, I will see an inconsistency on what's happening here. I'm getting 2 constant, nice, continuous arcs, and that tells me everything is going very well. If a point all of a sudden jumps out to lunch on me, I got to retrace my steps. 9, somewhere on that arc. Number 10, somewhere on that arc. True length of 8 to 9. From 8 to 9, whoops, is this distance. Here's the fall of 89. And here now is the true length of 89. From 8, I find 9. From 8, I find 9. And once again, it's running in a nice pattern with the rest of the points that I've located. From 9, I got to look for 10. From 9 to 10. That is my plan view. This is my plan view. Once again, triangulating over top of my total height. And there is the true length. Once again, back here. Oh, there's my 9. I must be looking for 10. Once again, traveling in a real nice pattern. Once you get into doing layout on things like Y branches and whatnot, and if they have mitered collars or a sharp miter, you will find quite often that the layout kind of goes all over the place. It makes a nice little wave starting at the center, going down and then coming back up on the wings. And when that happens, a lot of times we think, oh my gosh, I'm doing something wrong here. And in reality, there comes a time where we just have to start trusting what it is we do and believing in ourselves, and the end result is the pattern. A lot of times we don't know whether we're right or wrong until we actually lay that pattern out. I am now looking for 11 to 12, I believe. 10 to 11, sorry. There is 10 to 11. Here's the length of 10 to 11. I'm just going to stretch that out the bottom quite a bit so I don't lose it. And here now is my true length of 10 to 11. From 10, I get my 11. And next is from 11 to 12. There's my plan length of 11 to 12. Here it is plotted on my true length triangle. And now the true length of 11 to 12 right there. And from 11 to 12. 11, 11, 12, 12. Back to my 112 spacing. Somewhere on there, on these arcs, we'll find point 12, 13, I'm sorry. And somewhere on this line or arc, I will find 14. From 12, I'm going to look for 13. From 12 to 13 is that distance right there. 12 to 13 will be right there. And the true length of 12 to 13 is right here. And from 12, I find 13. From 12, I find 13. Document. 13, 13. 13 to 14. 13 to 14 is my seam. My seam is not straight up and down from each other. It is offsetting by the 1 inch as required on my working drawing. Here now is my plan length. I have to triangulate to find a true length of that. And that is right here. True length of 13 to 14 is this. And now I have point 14. Document. I'm out of numbers. Connect the dots. From 14 to 13. From 14 to 13. And I thought I'd take this opportunity to show how to use a French curve to connect these. A lot of times I'll just connect them by hand, but what I like to do is I'll just put it on the point I want to start off, and I'm going to swing until I get a nice something that works with my first point or so, or 2 or 3, and I'm going to go past the first point and stop there. Then I'm going to go back to that second point. I'm going to see if I can't connect a couple more. And that'll take me all the way to 7. I'm going to go just a little bit past it and start on my 7 again. Ooh, look at that. All the way through, it goes right to the 1. I can even go past there just a little bit, and I'm happy. Starting on the 1 again. Now I'm going to need to connect. Let's go back to here. There we go. Oh, that's so nice. Come back to the 1. 3, 5, 7. Look at that. All the way to that 7. I'll stop just shy and then stop back to the 5. Oh, look at that. I can go a long ways there. Slide this along. And there I have a nice finished arc. Do the same thing. Oh, there goes my keyboard. On the top, I'm going to find a spot on the French curve that will work for a few points, starting with the 8, for example. and I'm just going to go a little bit both ways. Back to the 8, and we'll carry that through to about here, back to here, connect it. Going the other way now. Put my start on that 14. Oh, look at, I can go past the 12 just a little bit, go to the 12. There's a couple more. I'll come back to there and stop. I'm just past the 8 and stop. Because of this being an oblique cone, there is no constant radius. We can't just use one arc. We have got to connect multiple radii together to get a finished pattern. And here I have my 4-inch round, and here I have my 7-inch round pattern, and this will give me a finished height of 10 inches. It will end up with a 1-inch offset here, or an oblique cone. A lot of times we find cones that are long and drawn out in dust collection systems or particle removal systems. In these cases, velocities are very important, and the fittings, the transitions are long and drawn out, and the reason for that is to keep them from plugging up. We make it using triangulation because we have an apex that is way far away from us. We can't deal with it. It's too far. Triangulation is the be-all, end-all. It takes a little bit of time. It's extremely accurate as long as we are accurate working with it. Once again, I am the Draft Doctor. Don't be afraid to hit the like, the subscribe, or leave comments. Have yourself a great day.